Hey, welcome back to another episode of Talent Tech Tips. And today we're going to go over a classic computer science algorithm, the Hanoi Tower, and how to implement it with Appian. Before we jump into the solution, let's look at what the Tower of Hanoi is. According to Wikipedia, it is a puzzle invented by a French mathematician back in 1883. And the reason that this works so well for a computer science problem is because by using recursion, you can break down the steps into a smaller collection of subproblems. And this is what computers do so very well. The rules of the Tower of Hanoi are to be able to take three different stacks and a variable number of disks, ever increasing in size as you go to the base on one stack, and moving it to a different stack with using one third stack as an intermediary position. And the rules are that you can never put a larger disk on top of a smaller disk. So in this example that you see here, we're taking and moving the smallest one first to the intermediate stack, the next bigger, moving it back, and then continuing this process until at the very end we have all of the disks moved to the other stack. I pulled out an example of Java code and how simple it is to solve it in those steps. So let's go see what it takes to do just the simple solution in Appian. So starting in the Appian designer, I'm going to create a new rule expression. We'll just call it the Hanoi Tower. And then we're going to add the 4 parameters in the algorithm and the number of levels we want to go down, the from, the to, and the auxiliary row. And we're going to give them a textual name so that we can refer to them later. So just giving some defaults into these parameters, we can test it and we can see that it does indeed print out what we had. The next step is just to add the logic as far as checking to see if we're all the way to the bottom of the stack, calling the recursive part of the Hanoi Tower, printing out or adding to the output the current stage. So if we test it, it's not going to work because we didn't save the changes. And since this is recursion, the save has to be applied before we get to see the finished. Even in low code, the Hanoi Tower is still easy to implement. The last example just looked at a log of the different steps in moving the pieces around the Hanoi Tower. Now what I actually want to do is I want to physically make a structure so that anytime during this process we could see what the structure is, and we can also add what the current state is when we log each event. So the first thing to do is we need a data structure, and I'm going to use a map for this. I found that maps work really good, better than dictionaries, because when you have an array of map, it's very easy to use, but if you have a list of dictionary, it gets a little confusing and you have to do some specific things like account won't work because you have one dictionary even though the dictionary contains many items. We're going to use a map. We're going to define different elements of it. And I want it to come out or be able to see the map when it's finished in this kind of output. So to create the data structure for our Hanoi Tower, we're going to use an enumerate to create the disks for the first rod. We're going to add 1 so we have numbers 1 through 4, and we're going to assign that to the first key within the map, in this case source. So let's take this formatted map and use it as the input to our first function. Our first function is going to be the tower move. So basically we're going to take a disk or a number from one rod within the map and then move that to another one. As long as the rod names within the map match our parameters, the from and the to, this function will run just fine because we index into the map based on those words. We're going to add one more output here so we can see what this looks like. So copy and paste the move value, and then we'll test this. And our output tells us that we indeed took the 1 off of the map. And if we look at the local variables, from stack has our 4 items from the map. Our to stack has null because there wasn't anything in that one anyways. So to take the move value and move it from the from stack to the to stack, we're going to use the update function. Now we got to use it twice because the first one is going to append the to stack, but then we have to use ldrop to get it from the second stack. So once we execute this, we can see in the output that we have indeed moved 1 from the from rod to the to rod. The last thing I want to do is add a trace. I want to be able to see at every move what the current disk stack is that we move from and to. And since we're storing it in the map, that's easy to pull out. Now that we have the function that moves a disk from one stack to another stack, we need to make the recursive function. This expression rule has our game board, it has a level number, and a stack array that gives us our different rod name. Since our expression rules always take a game board and return a game board, we have to make sure that our inner function passes back into our tower move that then passes back into our recursive tower process one last time. Since our recursive calls require the stacks to be ordered differently, we can take and manually order them, or in the case of the second stack, they're actually in reverse order, so we can use a reverse function for that. Also remember to save this before executing, since it's called recursively and the latest version has to be saved to call itself. We can test this and we can see it returns 15 items in the trace, including for each move that was made from one rod to the other, but also what's currently on the incoming and outgoing rod. In the last step, I want to make a function that initiates the recursive calls. That way it can set up my map for me, and also I can just have one parameter that specifies how many disks will be used. One last interesting point I want to talk about when it comes to the Hanoi Tower is the fact that the number of steps involved actually has a formula. 2 to the power of how many values you use minus 1. So in this particular case, there are 1023, which is 2 to the 10th minus 1, which means we've transversed and traced the appropriate number of output. If you found this helpful, make sure to subscribe for the next episode.